Welcome back. So it is my pleasure to shift the program now to be talking about, with our ATC 110 team, to talk about structural deficiencies. And as I mentioned, the technology comes in all different directions for evaluating buildings and analyzing buildings. So I'm going to introduce our moderator, John Heinz, who is Executive Director of the Applied Technology Council. Welcome.
Thank you, Janelle. So as Janelle said, I'm John Heinz. My panelists are Kelly Cobine, Vicky Bossier, and Andre Filiatro. Our topic is the role of technology in developing resources for improving structural deficiencies. And we've been asked to talk about that through the lens of the ATC 110 project. And so to do that, we thought you needed to have a little bit of an understanding of what the ATC 110 project was. So first of all, it is a major CEA-funded research and development project that includes FEMA support. We've been working on a 3-year project schedule on a plan that was written in late 2014 and was started in 2015, which means this year, 2018, we're going to be done. And the big goal, as you've already heard from Janelle earlier today, is the pre-standard for evaluation and retrofit of wood light frame residential buildings. And what does a pre-standard mean? A pre-standard means essentially it's seeding what we hope to be eventual standards or processes in the building code. And what we want to do in this pre-standard is essentially mitigate important deficiencies that we know to exist in residential wood light frame construction. But the important thing is we want to do it as simple as possible. We want to do it with pre-engineered prescriptive solutions where we can, and then we want to have engineering options where we can't. So the important thing here is there's a lot of people involved. You can't see all those names, but what I want you to see is a big blur of a lot of names because we just represent the tip of the iceberg of the large number of smart people working on this effort. And the reason why this project is relevant to the theme of this workshop is because we believe that the project is using technology in ways that have never before been possible. And that's what we want to show you today. Okay, we've organized our talk into 3 parts. The first part is about the analytical tools. The second part is about our engineering processes that we are using. And the third part is about our eventual results and the products that we've been developing. And as we've gone through the morning, I've observed there's been a certain rhythm to all the presentation, through all the panel discussions. There's been presentation, 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 then talk, talk, talk. Okay, we had a slightly different plan. Okay, so it's supposed to be a conversation. We took that very literally. So we're planning presentation, talk, presentation, talk, presentation, talk. So do me a favor, don't get too comfortable. Don't tune out thinking you're listening to a series of presentations because we're going to hear for a few minutes from our panelists. They're going to answer some questions, and then we're going to come back and we're going to talk. And if you don't talk, I'm going to ask questions.
Of the audience, not of us.
Not of us.
And if I know you, I might ask you a question. And if I don't know you, if I see you avoiding my eye contact and looking like you're otherwise trying to avoid me, I might ask you a question anyway, okay?
In school.
So our first part, I'd like to bring Andre Filiatro to the podium. And what I'd like Andre to answer for us is how have our analytical technologies evolved over the years, and what are we doing on the ATC 110 project that's special? So Andre, please come up.
Thank you, John. So to answer these 2 questions in 10 minutes, I thought first we'll look a little bit at a evolution of our capacity to conduct seismic analysis of light frame wood construction. and also try to convince or to show you that one of the very characteristics of this project was unique about ATC 110 is although the results are simple, simple plan set and standards, they are really validated by state-of-the-art numerical and analytical tools, and that's what I'd like to talk to you a little bit about. So if we look in the history, where do we come from in terms of seismic analysis of light frame wood construction? Well, as of 1983, there was actually nothing. There was no model dedicated to the three-dimensional analysis of wood frame houses. Not really surprising. I mean, 1983, March 8th, on that day, the IBM XT came out with his hard drive, 10 megabytes, with DOS 2.0 and so on. So it was just a start of, a numerical tool becoming sort of available before everything was mainframe computers. I remember software was using Strudel from MIT, for example. SAP was just a tool, a research tool at Berkeley with Professor Wilson. So not too surprising. What is more surprising is the next 15 years, from 1983 to 1998, if you actually survey the literature, you can find only 6 models or 6 studies on light frame wood construction that involve some kind of numerical modeling or structural modeling of wood frame. Among those, only one was able to conduct a dynamic analysis, which is obviously required if you have to have a good idea on the structural response during earthquake, and this was done at Washington State. So this is very different, a stark contrast, because during these 15 years, you could see that that's where we saw a lot of development in software. SAP became SAP 80, became SAP 90 at the time. Some of you may remember using that. That's really where software became available to practicing engineer, but still would remain relatively silent. 2 reasons for that, I believe. One, there was no demand to really conduct seismic analysis of light frame construction. And as was mentioned this morning, this is a complicated problem to analyze a light frame wood construction. The load path is not simple. We have to wait after the Northridge earthquake in 1998 to 2001, turn of the century, where the Curie Caltech wood frame project came about. And this was a direct response FEMA-funded project looking essentially at a better understanding of the behavior of light frame wood construction in the light of the damage that these structures and the losses that these structures suffered during an earthquake. Project was very comprehensive, was the first comprehensive research project looking at light frame wood construction. And out of that, many things were done. But in terms of the analytical side, 2 platforms came out of this: CASHU, cyclic analysis of shear walls, and SAWS, the seismic analysis of wood structures. These 2 programs were sort of complementary. The CASHU was able to do the analysis of shear walls. Basically, the idea was you had a predetermined deformed shape, how a shear wall deforms, basically in shear, and you assume that studs are rigid, the panels could deform in shear, rotate, move, and all the inelastic deformation concentrate in the connectors. So if you knew the behavior of the connectors, say sheeting to framing connectors, nails, and so on, that will be the input to CASHU. And then you can condense CASHU and make any wall lines that you've analyzed into an equivalent super element, like a spring, essentially, and then you can go and start analyzing 3-dimensional analyses of buildings. Certainly a step forward. So suddenly we're able to predict, for example, on the left, the response or testing of shear walls. So we're also able to predict shake table tests. These were the first shake table tests in the US on light frame wood construction, and you can see that we're able to predict that. So these programs were pretty good in the sense that we're starting to get an answer. They were used by practicing engineers following the project. These were all open source, Fortran-based, and so on, but they still have quite a bit of limitation. The software were simply based to analyze global response. What do I mean by that? Displacements, accelerations at different levels, and so on, but not the details. So it was not impossible to find out what's the axial force in a chord member somewhere in the diaphragm. Yes, you couldn't do that. Also, the software were really meant to analyze good detailed structures in the sense that if you have good hold down, the uplift was not too important, overturning was not too important, software is doing pretty good, but it was impossible to simulate uplift and so on. What was most important is if you look on this diagram on the left, the displacement capacity that was assigned to the elements of the software was relatively modest. At the time we thought, okay, we get to the peak, as you can see there, and we go slightly past the peak and say we lose maybe 20% of the strength and we call it quit. We say the subassembly has failed and so on. And we're now finding out that these assumptions were very conservative. Therefore, our predictions of response, and particularly when we move towards failure or collapse, was very conservative. Then came the NEAS program at NSF, so the Network for Earthquake Engineering Simulation program at the National Science Foundation. Several projects related to wood structure were founded, and one particular one, the NEAS Soft, ran from 2010 to 2014, developed the software called Timber 3D. And this was, I would say, a turning point where really now we brought the seismic analysis of light frame wood construction to the major league, if you'd like. There's a whole bunch of very fancy terms on the left, co-rotational formulation, P-delta effects. I'm just going to say here that this program, as you can see, the software, as you can see on this animation, for the first time, was able to reproduce collapse mode on light frame construction. So if you have a soft story, as you can see, we're able to follow essentially the side sway collapse of the structure all the way to physical collapse to the ground. We're also able to model the interaction between the different elements. So we can have a flexible diaphragm, we can model the uplift interactions between cords and frame members and so on. So in the end, this was the tool that was used in the ATC 110 project, because we believe, and we still believe, that this is at the moment the best tool available to analyze seismic, the seismic response of light frame wood construction all the way to collapse. By the way, this program was created at Clemson University. Professor Wenchen Pang and his team has been working for many years to develop this. So what have we done with this in ATC 110? What we did in the project, we developed models at different levels, essentially. We have simplified, intermediate, and detailed models, and these models have different objectives. So for example, a simplified model, as you see on the left here, which is a model of a cripple wall, was meant really to obtain global response. We're using a workhorse where we can carry thousands of dynamic analyses, incremental dynamic analyses, different intensities, and capture probability of collapse, for example. Intermediate was more complicated, where, for example, now we might be interested in modeling the in-plane flexibility of the diaphragm. We'd like to know what's the tension force on a chord member and so on. These models were also used in a dynamic environment, but much less intense, in the sense maybe you would run a few models under different intensity, but certainly not running all IDAs. And the one on the right, detail model, we go all the way to the nail. We have everything. We've got the nails, the frame, every stud is modeled. We use that occasionally. For example, in this example you see there, this is a model of a 4-foot cripple walls over an 8-foot one-story wall line, and we're particularly interested of looking at the continuous sheet of stucco on the side of the building. What's the influence of the continuity of the stucco? So the stucco is completely modeled. So the project has 3 levels of modeling. Also in the project, we explicitly consider residual strength. Some people call it the Kool-Aid effect. What is that? Well, here I've borrowed some tests that Eduardo Miranda and Greg Derline did during a NEAS project, looking at a particular form of light frame construction. And if I look at this loop there, many of you that have tested shear walls are very familiar with the loop. It goes up to about 3-4% drift. And we may say, okay, you have a reduction of strength, and maybe we'll model with a straight line, the post-capping straight line, and call it quit around 3-4% drift. Problem is, if you push forward, you push more on this specimen, you may get something like this. This is actually a test result, where at 10% drift, you still have 30% plus of the original capacity or the peak capacity of the subassembly. This has a huge impact of collapse probability or collapse performance, because it allows a structure at 10% drift to survive and not completely zero returning force. So this is an important point that we consider in the project, the capacity of the structures to deform realistically a very, very large level of drift. And all our models, including this, push envelope curves have a horizontal platform you see on the right, representing a certain level of residual strength. So I just want to finish the presentation, give you some ideas what we could do. These are simulations side by side of a house over garage model. On the left is an existing condition. On the right, the same structure, retrofitted, and you can clearly see, we can see a difference. You can see we can model collapse on the left, the retrofitted works okay. So we did that also for our hillside construction. This is a hillside running from 0 to 4 feet. On the left, again, existing condition. On the right, retrofitted. And you can see again, we have collapse on one side. We survive on the other side. I'll skip the next one for time. We have the same thing for cripple walls, which is the other model we looked at. What did we do with this? Well, we generated curves like this. This is a busy plot, but we took one model. This is a particular model, one-story house, 30 feet by 40 feet in plan, and the siding is this horizontal siding that we talked about this morning. Quite a weak structure. You can see these boxes on the right. There's 3 numbers that are showed. We're following the probability of collapse. You see a number there, 89.7%. This is at the risk-based NCE, 2% in 50 years, and this was our main criteria to look at. Almost 90% probability of collapse, not surprising. You have a cripple wall, you just have wood siding, basically very little strength. You have also 2 other numbers that we're reporting, the collapse rate at MC in the superstructure, collapse rate in the cripple wall. You can see in that particular case, all the collapse occur in the cripple wall. Not surprising, cripple wall is very weak. If we move to the middle, the 2 middle structures you see there, you can see an R equals 4 and an R equals 2. So these are 2 retrofit alternatives with different value of force reduction factors. So if the R equals 4, the lowest the R value, the higher the strength is of the retrofit is. So you can see at R equals 4, we're doing pretty good. We went from 90% probability of collapse to 38.7% probability of collapse. All the collapse occurred in the cripple wall. If we strengthen the cripple wall now even more with an R equals 2, we're still doing well, 8% probability of collapse, but now you could see that we're starting to migrate the damage to the superstructure because the cripple wall is getting stronger. And this was another aspect of the project where not only we're considering the main vulnerability or that we're looking at, in this case, a cripple wall, but we're also looking at the influence of retrofitting on the rest of the structure, of migrating damage to the rest of the structure. And I will leave it at that, and I'm not sure if I was on my time. I have a very bad reputation to keep time. John, did I do it?
You're a little over, but I'm all right.
Oh, man, I tried my best. Thank you.
Thank you, Andre. So as part of our presentation discussion rhythm, this is our first discussion session.
Oh, yeah.
So I'd like to open the floor to the audience. You have any questions for what Andre might have shown you? Because if you don't, I do. Here's one.
I'm afraid of that. Should I go back there?
One of the common construction practices for single-family dwellings in California is the stucco side of housing. And I'm wondering how much work you've done trying to ferret out how much structural, shear resistance stucco walls typically have, and then how much strain can they undergo before they begin to fall apart.
Right. Well, definitely in the ATC 110 project, all wall finish materials were considered. So typically stucco, wood siding, plywood, and also gypsum. So everything was included. When we would bid an archetype, we would consider the interior wall, partition walls, and so on and so forth. One thing also we've considered is when we have mixed sheathing, for example, if it's an exterior wall, say stucco on the outside, gypsum on the inside, we actually looked at test data of these particular configurations. So some test data that actually wall assembly, and we modeled essentially the behavior. So this was all included. Now to answer your question, do they have an effect? Absolutely. This is one aspect where non-structural elements has a huge influence on the response of light frame construction is a non-structural finish. I could even go as far as saying that if we were building light frame construction based only on the wood design elements that we're considering in design, we'd probably be in bad shape. So definitely the non-structural elements, stucco, gypsum, and so on, come and contribute vastly to the capacity, and that explained probably where the damage have been relatively modest compared to maybe what the early analytical study was showing. So huge effect.
That's reassuring because I have a stucco house.
Good for you.
Well, hopefully no one from the American Wood Council is here.
No, I
Neil-
checked.
Neil mentioned that earlier too about the failure. I don't know if I want, but about the failures in Napa too. That those were wood siding houses, so sort of supported
So
that.
another question, one thing you haven't mentioned, maybe it's just because it's not my field here, but how about lath and plaster? Was that considered? A lot of houses from
Yep.
pre-40s, yeah.
So-
well, I own one of those,
Right.
of course, I'm curious, but.
So the project actually was considering existing conditions as well as retrofit. And I think
Vicky will talk about
Vicky
it.
is going to talk about that. We did an exhaustive survey of existing houses going back to catalog by era, 1910, 1920, 1930. And there was, of course, in these era, gypsum didn't exist. There was the lath and plaster. And these, again, were considered in these models. So we had some test data, limited. But with the test data with that, we actually considered that in the models, yes.
So Andre, with all of the advancements and with the importance of non-structural finishes, do we know all we need to know to simulate wood frame construction?
Ooh, that's a tough one. Well, I would say that we have pretty sophisticated tool, right? We have the tool, but I'd say at the moment, these tools are, to some aspect, not tested, not verified, not validated. So for example, I mentioned early on that, for example, with the software we're using in the project, we have the capability to model hold downs or uplift from hold downs. We have this capability. We're able to model the interaction of the diaphragms between studs and so on. The problem is we don't have a lot of test data. So the validation becomes complicated, and I think we have to remain modest. And one thing was good in the ATC 110 project, we had a very strong, group of structural engineers that reminded us that what we're trying to do here is just help them with decision making. So we don't believe these numbers, we just use them as one of the criteria to make decision. So I'd say we're far from finishing off because we haven't validated a whole bunch of things. So it's like we have a brand new car, a brand new engine, everything, but we haven't really test drive it to the end. And I think experimental work will be required to do that.
So experimental work, a need. David.
I'm probably going too far into the weeds here, but after looking at stucco buildings during Northridge, for example, a lot of the performance depended on the quality of the anchors between the mesh and the studs. Were they corroded or not? Is that kind of thing the condition of the materials? How is that built into the model?
Kelly is a lot better for me to answer that question, but we decided in the project we didn't consider explicitly the degradations and so on. We looked at test data that was available, so some material was archaic and so on, but this particular aspect was part of the decision process, the engineering decision process. So okay, here's a difference of performance in behavior. When we generate fragility curve, we consider it for uncertainty. So we increase the uncertainty. There's ways to do that with fragility curves. So some of it was quality of the construction, but not explicitly. We didn't have a model say new stucco versus degraded stucco. We try to change property with high upper bounds, median, lower bounds, but we didn't associate specific level of deterioration. But maybe you'll hear more from Kelly a little bit later on that. Good.
So Andre, before we leave analysis, engineers of my vintage have been trained to treat analysis with skepticism. So you showed us all these very fancy analytical techniques. Can we trust these new analyses?
I thought he was on my team. Well, I think I answered that a little bit earlier. I think at this stage, these tools could be used by practitioners. They are open source. They're available, but it's not anything else. Garbage in, garbage out. So the level of sophistication increases, more chance of making errors comes in. And particularly in wood, just the intrinsic variability of the material make these analyses much less, I would say, certain than if I do a steel frame or something like that. So I would say I think it's important to have these level of analyses, but again, let's keep in mind they are there to help us make decisions, not to tell us that the probability of collapse will be 38.7 for that particular archetype. Does that make sense?
Perfect sense.
Thank you.
Please join me in thanking Andre.
Thank you.
You just took out 5 more slides.
So part 2 of our session, I'd like to invite Vicki up to the podium. And the questions I'd like Vicki to address are, what are the key deficiencies in residential construction that are being considered on the ATC 110 project, and how is the ATC 110 project using technology in developing resources for improving these structural deficiencies? Thank you, Vicki.
Thanks, John. So I not trip on these. Can you guys hear me? Can you hear me? Keep talking.
I can hear you fine.
Okay. John. So Andre's always a tough act to follow under any circumstances, but the fact there was a little overlap there, and I started with 30 slides yesterday, and they cut me down to 10. Now we're down to 5, Andre, just to let you know. So key deficiencies and what we've been doing in this project. When I started developing slides for this, I looked up technology, because I have people like Andre who are, I consider high tech. You know, we live in San Francisco Bay Area, and you know, we think of tech as high tech, but there was a lot of we'll call low tech that went in the development of this project too. So maybe I'm talking a little bit more about that, the engineering and the processes that we helped inform the analysis team, and what we did with it, what they gave us to help develop the product that Kelly's going to talk more about. So just to continue the historical a bit, all of us have been around for a while, so we know that historically engineering for single-family residence has been pretty nil. If you have a very complicated house or expensive, that's when the cost of an engineer might be involved. But even in the Bay Area, where you know an average house is, in my world, because I live in Eugene, Oregon, is over the roof. People, you know, the concept of spending, you know, more than $20,000 is pretty, you know, pretty discouraging for a seismic retrofit. So that's why, you know, this project that we've been working on, the ATC 110, to me is just mind-blowing. You know, I feel like it's going to open up an avenue to so many people who want to do this. I get calls all the time from homeowners, but just, you know, the cost of engineering is pretty much a deterrent. So, God, that's wobbly, isn't it? It's not moving though, so we're good. So I wanted to talk a little bit about deficiencies versus vulnerabilities. The deficiencies in residences are similar to any other structure. You know, I get a call about a warehouse building, you know, it's a tilt-up or CMU, and you've got wood roof, you know exactly what to go out and look at. Similar things, you know, you've got insufficient in-plane shear or out-of-plane bracing of the walls. The connections to the roof or floor are insufficient or non-existent. So similar deficiencies as residences. But we decided, very smart decision early on in the ATC 110 project, to approach vulnerabilities rather than deficiencies. So the 4 major that we're looking at currently are the cripple wall, house or room over garage, hillside, and chimneys. You know, cripple wall, house over garage, hillside have all of those deficiencies that we talked about. But by approaching a vulnerability, we thought we were getting more bang for our buck. And it's also considering our audience, considering that user that we talk about. I have a contractor who used to always laugh when I talked about overturning. He'd say, "Vicki, what? You mean like cow tipping? You know, what is that?" But if you talk about a cripple wall house or house over garage, people know what that configuration is. We know historically that they've had issues. So again, getting more bang for our buck if we're addressing those vulnerabilities rather than deficiencies. So Andres talked about this amazing analysis team, an analysis that they've performed on models. So what did we do with that, and how did we help inform their decisions when making the modeling? So we did some massive historical building studies. We also talked about the test data and how we were able to take available test data by other groups and use that to model our existing materials. Whereas if I'm doing a retrofit on my own, we're just ignoring the existing materials. But when we talk about getting to the final answer, which of course is the final retrofit, there's a lot of parts and pieces that came into our decision making. So there's the analysis work where we improved collapse performance. There's the ability with our new modeling system, Timber 3D, amazing program, to show that we weren't creating, migrating damage elsewhere. So we weren't on a cripple wall pushing damage up to the superstructure. Or if we're just taking care of a garage on a house over a garage, we weren't forcing damage either upstairs or other parts of the lower floor. And then we also looked at constructability. So, when we do these prescriptive designs, whether it's a plan set type format or an engineered, simplified engineer, we want to engage the most number of people in these retrofits. And so constructability was a huge part of our decision making. So a little bit about that historical building study. All of the groups in the ATC 110 project started by doing surveys of our available stock. So everyone you knew, go out and take pictures, see what we've got, see how many different configurations, how many buildings there are that actually match these vulnerabilities. But then when we got to the modeling process, we needed to come up with, rather than model, 84 plus 56 for the cripple walls, we needed to come up with medium structures. So we talked about all those different existing materials and how to come up with one which represented, more a median structure, a median minus beta, I'm going to call it median plus beta, so that we could make the best of our analysis time. And so based on all those studies of different sizes, different materials, different ages, different eras, we came up with a method of coming up with that median buildings for our modeling using average strength to weight ratios for masses for the whole structure. Also looked at 1- and 2-story buildings. And so the next part of that pie was the compiling with test data. So we were able to take all of these tests from previous projects and create hysteretic properties for modeling in the Timber 3D. And so then we went on to collapse prevention. So this is from the house over garage structures and room over garage. And so we've got an R factor here, and I assume that everyone knows when we're talking about R factor, we did an engineered design based on a code level using an R factor, and then we handed that off to our analysis team, and then they modeled that to see the results. So when I say of R, 6.5 and 5, those were the engineered designed Rs. And then we modeled different configurations, different building weights, different retrofits, and to get a probability of collapse for those retrofitted versus the base structures, and looked at percent improvement. So what we learned by this is, A, we can greatly improve the performance of the structures just by taking care of a localized vulnerability. So then we got to, so how do we take this information and turn it into design? A plan set or a method to design prescriptive. So all the different working groups had different assumptions because our buildings tend to behave differently. And this comes around to the constructability portion of this. So for instance, house over garage, we were trying to minimize the amount of foundation work that had to happen because we, again, that's a big cost in retrofitting. So we tried to pick walls on sidewalls that were a certain length so that we wouldn't have to put in new foundations. And so this is sort of that process. You know, we weigh our building. We came up with sort of averages, heavy, medium, light. We went through the analysis on different size buildings. And then we figured out how many we could construct under these circumstances. And actually, this is for the cripple wall buildings, and we started with a certain R factor based on our analysis. And after going through the constructability issue, we ended up changing our R factor for our prescriptive designs. So again, just how important it is that all of these processes, so not just the analysis team and not the engineering, but constructability being a huge portion of that, because we want to make sure that we can involve as many retrofits as possible. I think that's all I got.
Thank you, Vicki. So are there any questions about our design process? Any questions for Vicki? While we wait for the mics to go around, Vicki, I have a question for you. So we're dealing with a subset of deficiencies in residential housing. Are there other deficiencies that are common that should be considered?
Absolutely, I have a few. I don't know if anyone else wants to try, but we looked at some early in the project, actually, but because the variance was such, we ended up having to let's set those aside for a bit. Like house over garage and cripple wall tends to have a lot of overlap, and you'll also get split level houses. So we took that out of the scope for now. What else do we have?
What's your understanding of why we took that out of scope for now?
Time or dollars or no? There's just too much variables. It's my understanding of that.
Low-hanging fruit, bang for the buck.
Yes, absolutely.
Okay. There's a question from Bill.
So what did you find out about chimneys? Reinforced, unreinforced, well-connected, not well-connected?
Come on,
effect
Brian.
structure?
He's hiding under the table. Actually, that's probably one of the most developed of subsets that we have now, and Brian's done a lot of work.
Brian can say
Brian can answer.
Yeah, Brian was in charge of that.
So I'm the lucky person who heads up the chimney working group of this project. We had
Vertical mason.
a number of meetings with, I would say, seven or eight people on our task force. We never got a consensus once on anything that has to do with chimneys, except for the fact that they're likely to collapse in an earthquake. Strap them to your house. Is that good? Some people thought so. Some people thought, no, they'll just pull out a bunch of framing when they go down. Reinforce them? Is that good? Well, no, because if you don't reinforce them, when they collapse, they end up in lots of little pieces, and it's easy to clean up. If you reinforce it, they come down in one piece and do more damage and harder to clean up. So it's very difficult based on what little studies, I think Andre was talking about the paucity of wood frame damage prior to the Curie studies. There's not much analytical out there on chimneys, but we determined it wasn't really feasible to retrofit chimneys to get the kind of performance that we're talking about that's implied with new code construction. So the big decision on chimneys was, do you demolish them now and put up a light frame chase, or do you wait for the earthquake to demolish it for you and then put up a light frame chase? So I think that's sort of the consensus on chimneys.
And hopefully not fall on your neighbor.
a few more words on that. We chose the priority vulnerabilities that we wanted to look at, and as mentioned, we had cripple walls, house or room over garage, and the hillside, and we took on the chimneys. The cripple walls, house or room over garage, and hillside, we went into very extensive numerical studies using state-of-the-art software, collected data, and everything like that, because we really wanted to come up with very firm guidance on what a retrofit design looked like. We did not take the same route with the chimneys. We recognize the huge difficulty of doing any realistic modeling of them. Brian did try very hard to come up with some limited studies, but basically they were treated differently, and the outlook of the group was very much along the lines of best practices for damage limitation, extreme hazard mitigation from falling hazards and things like that. And so they were treated differently by the project.
Nothing in Timber 3D.
No.
No, we did not try Timber 3D on that, and the variables are pretty amazing because you start with, you've got this very stiff, brittle element, and you put it down into the soil, and you start thinking about what in the world you're going to say about that soil interface and how the chimney responds with the soil, and suddenly you've got this soil structure interaction thing going on, and houses want to flex. Wood houses flex a lot under earthquake loading, and we weren't quite sure whether the chimneys were pulling the houses or the houses were pulling the chimneys, but it's a very, very complicated interaction. And so Brian did a whole lot of really good work on the best practices for hazard mitigation.
And we did not follow up with what Kelly said. Is the bad news is they're almost impossible to analyze. The good news is we sort of know the answer already. They perform horribly, and it's mostly not feasible to try to retrofit them to modern standards.
And we did not model them as shear resisting elements either in our other structures.
So the project had to deal with a very important philosophical dilemma, and I'd like to pose that philosophical problem to this group. So Vicki mentioned it in her design presentation. She had to worry about designing the retrofit in a way that didn't propagate damage to somewhere unexpected in the structure. And Andre showed in his presentation what many folks have expected for a long time. Depending upon how strong you make the retrofit, you might propagate damage into an upper level of the structure. And Andre showed you that there's a bit of a balancing act going on there. You can reduce the overall number of collapses in the system overall, but you might increase the number of collapses in a living space versus the cripple wall space. So the philosophical dilemma is, what's better? Reducing the overall number of collapses or keeping collapse out of the living space at the expense of allowing a few more cripple wall collapses?
And so our structures are very different. I mean, the house or room over garage is a sort of different story because you can have living above and below. So we were sort of trying to balance that, whereas the cripple wall,
Well,
you're not living
wall,
below it.
Yeah, the likelihood of injuries or losing life if
Right.
a cripple wall collapse is very low compared to if you have collapse of the superstructure, clearly.
So any opinions from the audience on this dilemma? Who's avoiding my eyes? Christine has a comment.
Hey, I'm almost deflecting here, but not quite. So have you guys considered the type of roof? Because if you have the old tile roof that's really heavy, that's the question's going to be very different versus just an asphalt. So it's kind of a follow-up.
Yeah, so I don't know. So
I'm not going to let you get away with it, but go ahead.
So I mean, we did groupings. I mean, so many different options to come up with heavy, medium, intermediate, and some of them do have really heavy roofs and light floor walls. So we definitely did, and especially in the modeling analysis, we had exactly that thing: heavy roof. So we've done some scoping out of roofs over 12 PSF for that reason.
In the study of the existing building, you're using catalogs and so on. The weight was obviously a factor, so weight to strength to weight ratios, for example, and we came up in different configuration, heavy, medium, light. So although we didn't model the details of the geometry of the roof or anything like that, there was the weight, heavy, medium, and light, so that was considered.
But to follow up on John's question, I mean, that's going to change how you're going to, the level of damage you expect,
Sure.
right?
Absolutely.
So the simulation you've shown, for example, the archetypes I showed you, it's called a medium minus beta. It was a very weak one because it was wood siding. Most of it was no stucco or anything like that, and the weight was average was a medium weight. But of course, if you increase the weight on top, then things can change for different value of R, for example. But that was sort of built into all the statistics we were looking at.
Not speaking directly to the roof, but one of the things that comes out of this is that the heavier wall finishes that make the seismic mass higher overall, the stucco on the outside and the plaster over wood lath on the inside, actually inherently have more strength as long as they're in reasonable condition. And so you get some sort of compensating effect there. The Spanish tile roof at 20 pounds a square foot is one of the things that's an anomaly that clearly creates higher seismic mass, will create lower performance than other roof types.
And it's really when there's the transition from lath and plaster to gypsum that we see a fall off in strength. So a lot of the model, I was shocked personally when we did this study because in 1910, 1920, so many walls everywhere that the strength, base shear ratio, something like over 1.5, very high, very strong. But of course, if it's on cripple walls, not very good news. But the superstructure was very strong. And it's when, around the 60s, when the transition, when gypsum came in, then strength started to go down because the material was not as strong as lath and plaster.
And when we started getting into the design, spreadsheets, literally just massive, considering all of those things, considering what the interior walls, what the exterior walls, what the floors were, what the roof, to come up with combinations and.
But the slide that Andre was showing at the very end of it, he was looking at sort of the weaker end of the buildings that we analyzed, and it was made weak by the horizontal siding, wood siding on the outside and gypboard on the inside. It wasn't the lowest number of interior walls you could get, but it was fairly weak. As we went through the retrofits, the worst case retrofit was winding up with one collapse shifting up into the superstructure on weaker end of buildings. And so I think the answer is, from a safety standpoint, by and large, you can do a pretty rigorous retrofit and not have collapse move upstairs. There's an additional question of maybe it isn't collapse, but maybe I get a lot more racking and there's more damage to the finished materials upstairs. So it's complicated, but I think we saw fairly good news in terms of the vulnerability of the superstructure, and we have good news in terms of the ability to do rigorous retrofits that are going to have good performance without a very significant moving of very collapse or near collapse into the superstructure.
Looks like
John,
David has a comment.
Further take the bait with your question.
There you go.
I think it's a matter of risk, and you think about it. I mean, we've seen old houses fall off of their 18-inch little cripple walls and just go boom, and then they're stable as long as their gas lines aren't ruptured and other hazards. And I've seen houses up in near Eureka that came off the foundations, and we gave them a yellow tag and let the people stay in the buildings because they were still safe. They'd already done as much collapsing as they were going to do. So I think it's really a matter of risk. What's the consequence of failure? So sometimes it's okay to let the cripple wall go. It's kind of a fuse, if you want to look at it that way. And you're not going to get further damage. It is going to be dangerous. Now, you got to look at it from the economic side and what's the repair cost, but we all are supposed to be looking at safety first, of course. So those are my thoughts.
Thank you, David. Any other opinions? Looks like Charlie has an. Shauna, did you have a comment you want to make?
Yeah, well, I think Kelly actually addressed it, which was in one regard. I think that the answer to your question is pretty obvious. Lives are better or are more important than dollars paid out. And so clearly you don't want to be putting people's lives in danger by a retrofit that's designed to reduce an insurance payout. That's ludicrous. But I did love to hear that you had good news, so wonderful.
I'm sorry, we couldn't hear what you said.
Basically, Shauna said the answer was obvious. Lives are more important than insured dollars lost. So clearly, we don't want to do retrofits that are going to cause additional risk to life, even at the expense of more losses due to damage. Charlie, were you going to make a comment?
Well, how many people have died in the last 100 years of earthquakes in California in wood buildings?
We've
How
been
many?
asked this before.
Is that a rhetorical question?
It is. It's about 20. So 20
17?
in 100 years, the money is something around 200.
16 and
2 billion, 200 billion maybe. But they're pretty safe buildings even when they come apart. 16 were in the Northridge Meadows, right? That's the biggest single loss.
16, yeah.
Pretty safe, but we still want to retrofit.
You don't want to make it worse. I'm just saying.
Absolutely.
Potatoes compared to all the other places in Hawaii.
Right, and certainly when you compare the vulnerabilities that we looked at, the hillside, the house or room over garage, and the cripple wall, across the board, we feel like the cripple wall is less of a life safety issue than the other two. But certainly, if you're in your house and it slides down the hill.
Okay. Looks like Janelle has a comment.
I can do this on a microphone. One of the things that was amazing about what they tell me about the living space over garage is there's no benchmark. Whereas we look at cripple walls as pre-1979, we still have code-compliant buildings with living space over garage that are not safe, they're not damage resistant. And that's what I heard. I just want to hear you guys say I heard it right.
You didn't hear that today. You meant
In general.
Exactly.
In other
During
meetings.
our ATC 110 work together. And I think that's the big deal that we as a community need to work on next.
And I think true of Hillside Pumps too. We've had this discussion a lot lately because I don't know about everyone else, but especially since I've been working on this project for 4 years, I mean, walking around my neighborhood and watching new Hillside homes going in, I'm like, that's not anchored into the uphill, So yeah, we're hoping that, long term that this informs new construction. Absolutely.
Okay, please join me in thanking Vicki. So for part 3, I'd like to bring up our third and final speaker, and I've asked Kelly to address the following questions. How is technology making it easier to retrofit seismic vulnerabilities at scale? And what products are being developed on the ATC 110 project to help? Thank you, Kelly.
Okay. Thank you very much, John. And again, looking at this through the lens of the ATC project and the work that we've done there. And I have taken Andre's lead in looking a little bit at historical context. And while it's true that in some of the earlier earthquakes, we did see some damage to wood frame dwellings, wood frame buildings, and there was some discussion that came out of it. To me, it really was the 1-2 punch of the Loma Prieta earthquake and the Northridge earthquake that made it incredibly obvious to the engineering community, to the community at large, I'm sure to the insurance community, that there was this vulnerability of wood frame buildings that we weren't used to worrying about. So suddenly we're thinking about vulnerabilities and we're thinking about interest in retrofit. And so the idea of retrofit really has sort of proceeded along the two general paths of the general engineering methods and the vulnerability-based methods that Vicki was already talking about a little bit. The general engineering methods are methods, those of you that are familiar, it might be ASCE 41, it might be the International Existing Building Code or California Existing Building Code, or it might be simply using the new building code for retrofit. In general engineering, you're using design tools and procedures that apply across all materials, all building types, all building sizes. And the general outlook there is that you're doing this full top to bottom concept of what is the capacity, what is the demand, is it okay? And I've got the figure up there from the Home Builder's Guide that takes the 2-story wood light frame building and shows you all of the potential slip planes or places where you have to think about demand to capacity in this general engineering method. And so if you go down that road of the general engineering method, it starts out full building top to bottom unless the engineer comes in and based on their own judgment identifies some smaller scope. It relies very heavily on the knowledge of the engineer. It does not focus on the most efficient scope and method. It isn't looking at benefit to cost or anything like that. It can be costly, inefficient, disruptive, and fairly difficult to encourage, particularly in the wood frame residential arena that we're very much interested in. So the other route is the one that Vicki has already talked about, vulnerability-based. We're going to take past earthquake performance. We've learned a lot about configurations. It really comes down to configurations that are vulnerable to earthquake damage. It takes advantage of our past experience and our collective knowledge, provides high benefit to cost ratios. I think I have that backwards in the slide. We can simplify it, distill it down to simplified engineering methods, prescriptive methods, and things like that, that encourage very wide use. And so we in the project went very much along this vulnerability-based line that we thought could get much wider exposure. So what do we have in the way of past products that are looking at this vulnerability-based method? In these plan set or prescriptive rule of thumb types of designs, under the cripple wall, brace and bolt, that we've been talking about quite a bit today and most of you are very familiar with, there is some past guidance that's been out there, particularly following the Northridge earthquake. I think there was a RRR committee that got started and we got Uniform Code for Building Conservation Provisions, IEBC. There's a FEMA plan set, there's Bay Area Plan Set A through Association of Bay Area Governments and others. And a whole lot of local building departments have developed plan sets to take the idea of the cripple wall bracing and bolting and turn it into a very usable format. And so we've got a very good starting point for our project's consideration of those. Chimney, there are a few things that have come out, I think starting from City of Los Angeles. After the Northridge earthquake put information out, City of Napa has put information out, and I think a few other local jurisdictions, and there's also a FEMA document. They are focused on repair of damage post-earthquake, but they're equally usable for retrofit. And so they are the guidance that's out there right now, and they provided us and Brian over there with a starting point for what he was working on. House or room over garage, there really isn't any precedent addressing that in the 1 and 2 family dwelling arena particularly. We have seen the softer weak story provisions for the multifamily residential, similar in concept, but hard to necessarily scale down to the 1 and 2 family residential. Hillside dwellings, following Northridge earthquake, City of Los Angeles got in there and put together a voluntary standard for retrofit of hillside dwellings. And unfortunately, it never really got any traction past the City of Los Angeles. So it provided us with a concept to start with in this project. So sort of a range of different things there and not there and different uses that we had as the starting points. So we started with all of that good information and a project goal of good retrofit provisions that could be very widely used, coming very much from Janelle and her vision of we want to get out there and retrofit every single dwelling that we can here in California. So focus on the most effective retrofit scope, use of best available performance-based technology to optimize retrofit design, and we've been hearing quite a bit about that, Andre and Vicki. That is all going to be baked into what we eventually distill down into retrofit design in its most readily used form. And we have Tom Anderson, a contractor that's been working with us on the project, and what he has told me over the years is that he's done probably many thousands of retrofits in the Northern California area. And ideally, he goes in there and he works from a plan set. He does plan set A or the California existing building code version of it or whatever. If it is a complicated configuration that needs an engineer, then out of every 10 homeowners that he says you need an engineer, 9 are going to walk away. And only 1 is going to go through the extra complication of having to hire an engineer, have to go through the process of design, and then turn around and get it bid by the contractor and so forth. And so we have gotten the message very loud and clear that it is important to have as many of the retrofits as possible go down to a prescriptive provision plan set sort of implementation that does not involve bringing in an engineer. We also look very much at simplified engineering methods. So when the engineer is necessary, they can spend 90% of their time figuring out the detailing and doing construction oversight of it, and 5 or 10% of their time doing calculations. We can simplify it down to very simple calculation rules, and there's no reason to go into that in any great depth. So new products that we're putting forward, vulnerability-based methods, plan sets, and prescriptive provisions written out like the IEBC provisions are, and simplified engineering for all 4 of these different categories that were our priorities that we agreed to start with. So first up, the brace and bolt. We are coming out with a new series of plan sets for the brace and bolt. We decided to go through our performance-based numerical study in order to look at the performance of these and put forward what we think are a very solid, rational set of retrofit provisions for which we have some indication of the performance metrics. There were a couple of hanging questions that we kind of had to deal with when we did this. One is that the way that these were written into the earlier codes, for those of you that are engineering nerds, I'll say it wasn't clear whether you should be using an R of 2 or an R of 6 or 6.5 for the design of the cripple walls based on how you interpreted the code. For non-engineers, what I'll tell you is that the result of that was that there was more than a factor of 3 in the amount of plywood and nailing and anchor bolting that people might decide were necessary for exactly the same building. So there were some things to be settled out. We have moved to a performance-based design. We did trial retrofit designs. We benchmark what the performance of those retrofits are, and we now can put forward a recommendation for retrofit that doesn't worry about how you interpret the code. We're setting what it is that should be done, and we're speaking to what performance it creates. The other thing that we got involved in here very much was the hanging question of, if you go and retrofit, are you going to necessarily push collapse above? Are you going to push an awful lot of damage up to the story above? Or are you going to have good overall performance? And so we've taken a look at that, in, as Vicki has mentioned, incorporated that into our solutions. Here's to Brian's part, and we have a plan set best practices for retrofit of chimneys. As he alluded to, for the most part, that means making the brick masonry go away in various flavors, including bringing it down to the roof and capping it, taking it off to the top of the fire blocks down at the shoulders and rebuilding it in light frame with UL listed flues, and a variety of other choices here, and some very nice guidance that Brian has put together on that picture. For the house over garage and room over garage, we are putting together plan sets that will help this be implemented prescriptively. So not only are we going to take a first stab at talking about what the retrofit ought to be from an engineer criteria, but we're going to have the prescriptive solution also, and that's something that Vicki has been leading the charge on. We tend to be looking at the entirety of the lowest story for the house over garage and the garage portion for the room over garage. We're looking at reinforcing both longitudinal and transverse walls. If there's enough wall there to put plywood on, we've got plywood solutions, and we move into cantilevered columns and some of the proprietary shear wall products if you don't have enough room just to go in and get adequate plywood. And finally, we are putting together a plan set for retrofit of the Hillside homes. Following the lead of the City of LA, we have also reconfirmed that the important thing here is that we get a very strong, stiff anchorage of that home to the uphill foundation. And what you see here has this superstructure, the occupied portion missing, and what we're doing is we're going to either end of that first frame floor and we're putting a very strong stiff tie into the uphill foundation, and then we're supplementing it with a series of secondary anchors tying into the uphill foundation and shear. Simple structural realities here is that you start loading a structure and the load is going to find the stiffest load path out. And on these hillside homes, it is that uphill foundation. Very interestingly, we have found out that we also do get some good benefit for putting plywood sheathing and anchorage on the cripple walls that are on the downhill and step sides of it. And so we're actually encouraging both of those to be done. But that is our final retrofit that we've taken on.
Thank you, Kelly. So any questions from the audience for Kelly? Fred has one.
A bit of history, the Residential Retrofit and Repair Committee debated extensively over whether short crawl space walls back in the mid-1990s, whether short crawl space walls really needed tie downs. So which way are you? At the time we decided not to, we lengthened the aspect ratios of the walls, but what are you currently recommending for short crawl space walls in terms of tie downs?
So for the most part, we're trying to put together solutions that do not have tie downs. And certainly the shorter cripple walls, we want to avoid those altogether. There are two things. Colin Blaney is the one that has been heading this effort. And what his group is finding is that either because you've gotten a fairly tall wall, and it goes up to 7-foot cripple walls, and by the time you get to 7 feet, you've got a pretty good overturning potential on it and uplift. So as they get taller, it becomes more important. And the other is as you get very narrow buildings, you go to San Francisco and the houses are on 25-foot wide lots, and and Berkeley and other Bay Area places too. So you get a very small length of transverse shear wall. And so as you do that, you need to get higher and higher capacity out of that. And so either tall or high capacity, because you have a very narrow shear wall, will push you into tie downs. And so that was included in the FEMA cripple wall plan set that came out. And similarly, we are going to be allowing for tie downs when you need them.
Any other questions from the audience? There's one up here. While we're waiting for the mic. Kelly, I have a question. So I'm a structural engineer, and I believe in engineering. Is it really possible to take complicated engineering concepts and simplify it in a way that non-engineers can use?
So the answer to that is absolutely, and it has been done before. The IEBC Plan Set A, City of Los Angeles Plan Set, and all of the other jurisdictions. Basically what we're doing is pre-engineering the solution. Just like conventional construction that houses have been built with for many, many years. And so we, in this project, put together the retrofit design methodology first. We came up with the engineering method, and then we used that engineering method to pre-design the solutions. In order to do that, we did have to put scope limitations on because we want to be using them with the simpler building geometries and not huge dwellings. At some point, they go beyond the intent. But yes, the answer is yes.
If I can just add also a characteristic of this project is all these pre-engineer have been verified the performance through analytical studies and also constructability. So it's pretty exhaustive in the background, if I may say.
And I think, Andre, you mentioned on your last slide, too, that, these pre-engineered that may not fit the models or the designs that we did exactly, because, we can't pre-engineer every house out there. There is some conservatism in them. And if we're saying probability of collapse is 12%, maybe they're getting 15%, but it's an 80% improvement over what they had before. So.
Can we adopt these standards at the state level so we don't have to go to 500 jurisdictions in the state with potentially 4 new standards? And we've been talking about a soft story for multifamily. Do you think that's the opportunity to get this out there, or do you think we're going to have to go jurisdiction by jurisdiction?
So the precedent there is that the state of California did adopt the IEBC Appendix Chapter A3 cripple wall retrofit provisions into the California Building Code. It's not triggered, but it's sitting there as the model code, and people are pointed to it as an appropriate measure. And so it would seem that we could potentially do the same sort of adoption of new information at the state level, going through the state code adoption process.
Yeah, could I state that is in fact our goal, is to have it adopted into the IEBC. It is important to say too that this document is intended for use throughout the United States, not just in California.
I would like to compliment you. For those of you who aren't engineers, you have no idea how difficult it is for engineers who are used to calculating everything to 3 significant figures to come up with general prescriptive designs that are going to be applied by non-engineers. But I think that was, as we've heard over and over again, most homeowners aren't going to go out and spend money to have an engineered design. So I think the coming up with prescriptive designs that are going to vastly improve the performance of a large number of houses was a significant accomplishment of this group. And part of the reason for doing all the analyses was to get the engineers comfortable with the idea that we actually could zero in on some reasonable prototypes and improve the performance. It's not going to be perfect. These aren't going to be as reliable as nuclear power plants, but they're vastly going to improve the performance of residential structures with vulnerabilities.
Thanks for the compliment, John.
Yeah.
Thank you.
One thing that I'm coming from the standpoint of the earthquake modeling business, where for the most part that business has been driven by claims data from the insurers themselves for earthquake damage, particularly on residential. And all this discussion here is based on engineering models. And I'm wondering, and maybe this is a question for Shauna as well as the CEA, but over time, the CEA is going to be getting claims data because they're paying for it, okay? And is there any effort, or any plan for the CEA to institutionalize, making that data available to like Timber 3 so that we could see how the engineering models, either on a total loss basis or on an incremental basis, by roof failures or floor failures or walls, compare what really was paid out. And I recognize it's not easy because claims adjustment's different than the damage estimates, but it seems to me that would be a very important thing to do.
Yeah, it is our intent to, in fact, Buddy and our research department is looking for opportunities how we can properly share not only this project but the Pure project. And it is absolutely our intent that this information is to be used by the community at large. Absolutely. Yeah, if we're not all looking at the same stuff and sharing, then, I don't know who we think we're serving, but we're with you on that.
Any other questions from the audience? Body has one.
I promise this time only a real question. Can you comment on, or can FEMA comment on the CEA comment on the rollout of the insights of this to people that you would like to have use it? So are there plans afoot to communicate the results and get these new plans in the hands and get that wide use that you're looking for?
The woman with the big smile over there, I think.
So the cool thing is this just so expands the earthquake brace bolt program because we have taller crawl space walls that can be done without an engineered design. So that will be rolled into as soon as possible into the earthquake brace and bolt. We have put in an application for FEMA funding to do what I call ESS, which is earthquake soft story. Maybe pick a target area, maybe San Francisco, I can't guarantee that. But to do a target, obviously a lot more expensive than earthquake brace bolt, not sure how much of a grant we would give, may need to also work with banks to come up with additional low interest loans or something. So we're absolutely excited to make these roll into incentive programs and draw as much attention to their publication in August? September?
Absolutely.
Oh, okay. I'm looking at you guys. Do I have the right
Contract
date?
expires in June, so yeah, we can make August, no problem.
As soon as they finish, Mike and I intend to try and take this into a model code, and then the CEA intends to try and expand our incentive program as much as we can.
So just following up on that, from the procedural standpoint, it goes from a pre-standard to going to a standard organization that's going to turn it into an ANSI conforming standard, at which point it could either most likely be referenced by IBC, IRC, and other codes, IEBC, or potentially it could be brought into the codes themselves. And so along with all of the wonderful work that CEA is going to be doing with it, it is intended to be made available on a nationwide basis through the model codes.
Okay, so my question is actually from Andrea, and actually with support from the peer people that use the office here, I wonder, as far as, Timber 3D, of course, is, or any other code, as advanced as it is and unique it is, it cannot be validated. But then on the question of verification or comparison with other codes, obviously there are no other codes capable at this time. But we have the other peer, CEA project, the peer project. Part of the activities in that project would be to look at the ATC 110 and not only look at those results, to somehow implicitly verify it or take it to the next level to damage, loss estimation. Now, of course, the plan there, as I understand it, is to use OpenSeas. Now, I wonder, of course, I think ATC 110 is not using OpenSeas yet, but I know they are collaborating or, specifically the numerical modeling groups with peer projects. Now I'm wondering in the longer run, especially because peer fragility projects are defining, more realistic index buildings, and they have a lot of experimental lab testing. So they are one step closer to physical reality. So is there anything in the work toward the completion of this project and the next to have some code what you get as comparing what you get from Timber 3D and then later in OpenSeas, assuming that OpenSeas becomes developed enough and assuming that they are independent.
Right. Well, a couple of things. One of the good thing, I think, for coordination between the two projects is there's one member of our team, ATC 110, David Welch, which has been one of the leader of all this analytical work, is now working for the CEA project on the peer side. So he knows everything what we've done, so everything has been exported very well. Now, I won't speak for the peer project because I'm not involved directly, but just talking with Dave, they are doing right now this kinds of verifications where they're taking some archetypes and verifying what Timber 3D is doing versus OpenSeas and so on. I mean, I don't know. I mean, what they're going to decide to do in the end. I suppose it's a peer project, so it'd be difficult not to use OpenSeas, I guess. But in the end, you can make OpenSeas do something very similar to what Timber 3D is doing. The only appeal of using Timber 3D is that it's been designed specifically for light frame construction. So you have very, I don't want to go into any detail, but some elements, for example, that you can reproduce in OpenSeas, but with more work essentially, and more, the model will not be as efficient. Now, in terms of verification at large with Timber 3D, we have had verification all along. I mean, it started with shake table test in Japan, for example, where we were trying to predict collapse and so on. So the program has been verified quite a bit on various type of configuration. Now, may not have been verified directly with all the specific configuration we've looked at. Cripple wall, I mean, I'm not aware of a shake table test of a cripple wall on the real stick models to collapse, at least in the United States. In Japan, yes, but it's completely different construction. So I think, yes, I think this verification is happening on the peer side. And in the end, I mean, the numerical model is just one component of the loss estimation. I mean, if you get a better model and you get particularly better data that goes into the model, then you get a better structural response, which is one component of the whole chains of P58 to get a better loss estimation and answer in the end. So I don't know if there's anybody from the peer project here. I think Youssef stepped out, but
Are you involved?
maybe Kelly could say something about it, and you're involved as well, right?
Or you may get a better hold on uncertainty or specific uncertainty if you are using more than one model.
Right. Yeah. But I know for sure that there is right now. I mean, I know on the peer side, they've started with Timber 3D, generated some results, and now I think they're going to try to make OpenSeas replicate those results, and then maybe continue with OpenSeas for whatever reason. I mean, that's their baby, so they're going to try to use it, obviously. You know.
Well, I'd like to add, though, that the choice of Timber 3D was a careful choice.
Yes.
It wasn't random.
No.
It was tested against other software. We investigated the other research software, OpenSeas. We investigated also engineering production software like Perform, and it went through a process where we decided which program we thought had the most capabilities for what we were trying to do and gave us the best information as a result.
Right,
so it was a careful process.
It was, but I would not go ahead and say that Timber 3D is better than OpenSeas. I mean,
I didn't say those exactly. I didn't say those words.
I understand, but I cannot say that. I'm just saying one of the driver for using Timber 3D is because it was doing what we wanted, but also very much focusing on the type of construction for the modeling. So a lot of shortcuts to make things faster. And with the thousands of analyses we did, we wanted to have the best efficient program. So.
Mike Mahoney.
I just wanted to add a couple things to what Kelly and Janelle said about how this is going to move forward and be distributed. Our I guess, model that we're following here is that the FEMA plan set for the cripple walls and the chimneys were actually recovery advisories that were published using South Napa disaster funding and were distributed as part of our response to that earthquake. So those are still out there. Those recovery advisories are available for future disasters. Our hope and intent is that the pre-standard that you're hearing about now in our agreement with CEA is that we'll publish that as a FEMA document as soon as it is done, given our government printing office delays and all that stuff, but you should see that by this fall. And then we, as Kelly said, we are now working to convert that into a ANSI-approved standard, and we're talking to the International Code Council, because they are an ANSI standards development organization, convert that into a standard that would then be presented into the code development process for future edition of either the International Residential Code or the International Existing Building Code. We're not sure which one yet, because it's a residential, but it's dealing with existing buildings, and that's kind of a gray area with the international codes. But right now, the only thing in there is the International Existing Building Code, Appendix A3. This will probably replace that. Our hope is, because it is a standard, it can be adopted by reference directly into the code itself. That may be a hurdle we have to take a couple cycles to get over. But eventually this will be in the building code for adoption by not only California but other states as well. And that is the ultimate end goal, to get it into the state codes where then it is used by all jurisdictions. So we're finishing the first step of the process. There are a couple more steps to go. But the material will be available come this fall for anybody to use as a FEMA document. So, thank you.
Thank you, Mike. There's still a couple more minutes. I have a question. We've heard a lot today about tools, and an important thing when you're using a tool is to make sure you have the right tool for the job. So we've been talking about prescriptive tools. I'd like to ask Kelly, when are prescriptive methodologies a good tool, and when should engineering be used?
Okay, thank you. Very good question. In order to confidently use prescriptive methods, we have found that we have to place some scoping limits on it, and I did mention that before. So unusual systems, very large buildings, very irregular buildings are not necessarily going to be well served by prescriptive provisions, whereas the more regular and smaller buildings are within the limits of what is standard within the residential building stock. And so there are very specific eligibility requirements that we've been establishing as the pre-standard gets put together that capture some of that configuration, weight, and so forth. The other thing to point out, and something that we're very actively talking about right now, is that the use of a prescriptive solution or a plan set for the hillside dwellings is somewhat controversial, and I think John Osteris talked earlier about the complication and the ability to sort of focus down to simple rules and feel comfortable with it. And the steep sites and the more complex foundations that occur on the hillside dwellings are one of the things that we're really trying to grapple with right now. I think within our project team, we have a group that is very confident that at least for simple hillside geometries, we can put out a prescriptive solution, whereas others are worried that you get into the hillside dwelling and you maybe have slope stability and erosion and other issues going on, just retained soil issues. So it's more complex, and someone with a hillside dwelling should just go get an engineer, and we can talk about what the retrofit concept is and what force levels ought to be, but it ought to be engineered. So it's an active discussion within our group, something that we're wrestling with and haven't necessarily completely answered in all cases.
Thank you, Kelly. And so with that, I'd like to thank the panel for all of your work putting together the presentations. Thank you all for your participation. As we've already mentioned, look for more results coming in the fall of 2018 to a theater near you. Thank you very much.